Okay, well, I'd like to thank the organisers for the opportunity to be back in Bangalore and to be here in front of this magnificent sweep of blackboard. The first two lectures are really going to be about just geodesic flow and negative curvature, and I'll get to the Weil-Petersson metric in the final lecture. And the general nature of what I've got to say is that there is a sort of standard argument for proving ergodicity of systems of this kind. Today I'm going to do it in the case of the geodesic flow for a surface of constant negative curvature. And then tomorrow I will move up to variable negative curvature. And then on Friday we will get to the Weil-Petersson metric, where the goal is to do the same, make the same argument work, but in the face of yet more difficulties. So the general nature of what all of the lectures are about is the idea that if you have negative curvature, that should lead, well, that gives rise to hyperbolic behaviour of the geodesic flow, and that tends to lead to ergodicity of the geodesic flow. This first step is really always happens. This step, not necessarily always. It's not so easy. Okay, so that's the sort of nature of all of the proofs. And eventually the idea is to carry out this scheme for the Weil-Petersson geodesic flow. But let's start with the beginning. I will sort of explain some of the words here. Perhaps I should begin by explaining ergodicity. So the idea is you have a flow on some space X, and let's have a measure mu that's invariant under the flow. Then we can say that mu is ergodic, or we could say that the flow is ergodic with respect to mu if whenever we have an invariant set. So this is a set which stays inside of itself when you flow it along. If this set satisfies mu of A is 0, or mu of its complement is 0. And so I can draw a picture. The picture that I can draw is a picture of what non-ergodicity looks like. So this is a picture of, it's going to be a picture of non-ergodicity. We have A and A complement. The flow restricted to A stays inside of A, does not interact with A complement, and the same here. And if both pieces are non-trivial, i.e. have positive measure, that's non-ergodicity. So ergodicity is the notion of indivisibility for a measure-preserving system. And you can also formulate the idea of ergodicity where you have a diffeomorphism acting on X instead of, or a homeomorphism instead of just a, or just even just a map instead of a flow. So I think the first example of ergodicity is that everyone learns, probably that the world learned, is irrational rotation of a circle. And I think maybe, well, I don't know whether the next example is the one I'm going to talk about today, but it was a very early example, the geodesic flow for a surface of negative curvature. Okay, so we have ergodicity. Oh, and there is another way of formulating ergodicity. So our flow is ergodic with respect to mu, that is equivalent to saying every invariant function let's say f from x to r is mu almost everywhere constant. And the class of invariant functions that I'm interested in is measurable functions, let's say bounded measurable functions. I won't bother writing the details on the board. And so at first sight, so it's clear that if this property holds, then you've got ergodicity, because the characteristic function of A of an invariant set is an invariant function. And this at first sight appears as though it could be stronger, because you could imagine invariant functions that aren't characteristic functions. But then you do the usual kind of argument that you do in measure theory. You start by thinking of characteristic functions, you move to simple functions, you move to general functions. And so if you just run the kind of machine that you learn to use in measure theory, you find that these are equivalent. And it's this formulation that's actually going to show up in when we come to prove ergodicity. Okay, so we have the notion of ergodicity. The next thing is geodesic flow. So I think that was explained. I can't remember now whether it was in lectures yesterday or the day before. But let's start with a geodesic flow. So, with apologies to Athanas, I'm going to have a Riemannian manifold. And I fear that from time to time I am going to actually use the curvature tensor. It's not really the curvature tensor I care about, it's the properties we can derive from it. So hopefully Athanas won't be too upset that I have a Riemannian manifold. Anyway, so here's a Riemannian manifold. You have a vector V. There is a geodesic, a unique geodesic, which I will call gamma sub V. And it has initial tangent vector V. It's the unique geodesic with that property. And there's a differential equation that the geodesics satisfy. And I can write it that way. Or maybe so prime denotes the covariant derivative along the curve. So the differential equation says you start off in the direction of V, you go straight ahead at constant velocity. So that means not only constant speed, you turn neither to the right nor to the left, not up, not down. To the extent that you can go straight ahead in a curving world, you do it. So and there is a unique curve starting from each V. And so the geodesic flow, which I will denote by phi sub t, acts on V, and it turns V into the tangent vector to this geodesic after time t. So we go distance t down the geodesic, and there is phi sub t of V. And so the thing to notice, the main thing to notice here is that phi sub t acts on the tangent bundle. It does not act on the manifold. So you do not want to write a paper about geodesic flow on a surface, because the flow is not on the surface. It's on the tangent bundle of the surface. And since the length of the vector stays the same, it's natural to restrict to the unit tangent bundle. If you look at vectors of a different length, you see the same flow, just running at a different speed. So very often you restrict to the unit tangent bundle. Okay, now there is something called the Liouville measure. It's going to be denoted by mu. So it's a natural smooth measure. There is Liouville measure here, and then you decompose the measure here into the measures on each of the tangent bundle. So I guess T sub R of M is the set of V with, norm V equals R. You just restrict the measure to these guys. So the restriction to T1M of the Liouville measure is again called Liouville measure and will be denoted by mu. Hopefully it will be clear which context I'm using mu in. So this is a natural smooth invariant measure. And I'll tell you what it is in a minute. And in particular, it assigns positive measure to open sets. Well, non-empty open sets. And so before I tell you about mu, let me just show you a consequence of ergodicity. So a geometer might wonder, why should I care about geodesic flow being ergodic? I want to know geometric things about geodesics. So here's a proposition. What does my proposition say? Yeah. If the geodesic flow is ergodic with respect to our Liouville measure, then for mu almost every unit vector, if I look at the set of tangent vectors, all tangent vectors to its geodesic, this set is dense in the unit tangent bundle. So if I have a surface with ergodic, for which the geodesic flow is ergodic, if I pick a vector v at random, its geodesic is going to go around and around, probably not exactly like that, but if you pick any point, any direction, it will go by very close to that point, very much in that direction. And if you think about the familiar surfaces with constant negative curvature, sorry, with constant curvature, think about the round sphere. Geodesics there, well, there's the typical geodesic. They all look like that. No way on earth is this geodesic flow ergodic. If you move up to the flat torus, think of the square with the edges identified. If I go at an irrational angle, I end up with nice dense geodesic. But this is density only in the surface. You're always going in the same direction. This geodesic never gets to go that way. So this is a non-starter for ergodicity as well. Negative curvature is a different story. If you want ergodic kind of properties for the geodesic flow, it's negative curvature that you want. So, okay, so let's prove this proposition. So let's have some open sets, and this should be a countable basis for the topology of the unit tangent bundle. And now for each one of these sets, I define a related set. This will be, I could write it as the union over T in R. Maybe I'll write it as phi minus T of UI. And this is equivalent, another way of saying this is it's the set of V, set of unit vectors such that phi sub TV is in UI for some T. So it's immediately obvious from this definition that this set is invariant. It's a union of complete orbits. It's the union of all orbits of the geodesic flow that go through UI. So it's an invariant set. And obviously, UI hat contains UI, which is an open set that's non-empty. This has positive measure. That has positive measure. We have ergodicity, positive measure, and this is an invariant set. So positive measure for the invariant set means full measure. So mu of ui, let's say ui hat has a full measure for each I. Now you intersect all of them. This also has full measure. So almost every vector lives in here. And if you're a vector in here, your orbit under the geodesic flow goes through every single UI. So that's the proof. It's a very simple proposition, but it gives us a nice geometric flavour to what ergodicity of the geodesic flow means. Okay, let's make some space. What comes next? Yeah. So now I think I want to move towards telling you what this invariant measure is. Apologies to the people who already know, but I think it would be worth saying what it is. And also we'll introduce some ideas that you use in thinking about geodesic flow. So really I want to talk about some geometry in the unit tangent bundle. Well, and to some extent the tangent bundle, and to some extent the unit tangent bundle. So that's my effort at writing the Greek letter xi. Xi has quite a lot of wiggles in it. So I make sure my xi has lots of wiggles. This is going to be a tangent vector to the tangent bundle. So it's got a foot point, which is a v. So here's a picture in the tangent bundle. V is an element of the tangent bundle. It's not a good idea to say that a vector is a point, even when it's a point in the tangent bundle. It just gets me confused. So we have our V. Xi really looks like a vector. And then what's the point of a vector? Well, it's tangent to a curve. So we have some curve, v of t. So little v is big V of 0, and xi is the initial tangent vector. So this is a nice abstract picture. It's great for sort of conceptual understanding, I guess, but it's kind of useless for actually doing anything. If you want to do things, you go down and draw a picture in the manifold EM. And having done things with that picture, you can then go back to the conceptual picture and maybe think about what it, contemplate the meaning of it. So here's a picture in EM of the same thing. V has to have a foot point, which I'll call P. Oh, and our tangent bundle has a projection, which I'll call pi. So hopefully I've identified the symbols that are going to come up. So now we have a point P. We have our vector V. Now it looks like a vector, because this is in EM. And now we have our curve of vectors. Well, there's a curve. It's not that curve. That curve looks like this. There's V of t, and that's V of 0. And we can define C of t, which is pi of V of t. So this curve here is actually C of t. So that's the picture you can really think about. And then if you look at this, if I look here, there are two things I can think about. I can think about the tangent vector to the curve, and maybe in the first week of here, you all learned about the covariant derivative. So there's two pieces of data I can write down. I can write down the tangent vector to the curve of foot points, and I can write down the covariant derivative of the vector field along the curve. So by the way, a vector field along a curve is a curve in the tangent bundle. Just thought about in a more useful way, but they're actually exactly the same thing. And this curve it's conceivable that this curve isn't going anywhere and the vector's just moving around in a single tangent space. But it still fits. So our tangent vector to big V at time t corresponds to this pair of things. And so if I think about t equals 0, I have the initial tangent vector, which was xi, and this corresponds to c dot of 0 and the initial covariant derivative of v, which maybe I could write this as, oops, that should be at 0. I could use dash to denote covariant differentiation. Dot is just natural differentiation. This is using the connection. Okay, and then it's pretty easy to see that c dot of 0 is actually the derivative of the projection pi applied to the vector xi. As we move in the tangent bundle, when you project down, you've got c moving along. The derivative of the projection takes this tangent vector to the tangent vector of c. And this thing is given a name. It's called, I'll use kappa. That's my effort at writing kappa. So this is just by my definition of kappa. And so part of what I'm saying here is the claim that if I were to use a different curve that has initial tangent vector xi, it's pretty easy to see that this is always going to be the same. This also turns out to be the same. You have to make a calculation to verify it, which I'm not going to do today, but it's true. And then this we call the horizontal part of xi, and this we call the vertical part of xi. So here V stands for vertical, up there it was V for vector. And so you have this correspondence between xi and its horizontal and vertical parts. Xi was in the tangent space, so the tangent bundle at V. What we get here is a pair of vectors at the foot point of V. And thinking of the pair of vectors is usually a hell of a lot more helpful. Well, if you want to calculate anything, it's usually a hell of a lot more helpful to think of the pair of vectors than xi. Sometimes for understanding what it is that you're actually doing, this is the helpful picture. You want to be able to slide from one to the other at will. Okay, so we have that. And so the tangent space at V is sort of isomorphic in this way to that. And if I want to do, let's suppose that V has length 1, so it is in the unit tangent bundle. What's the tangent space to the unit tangent bundle over here? Well, this first component tells you how the foot point of your vector can be moved around. So you can do anything you like with the foot point. The second component tells you how the vector changes as you move along. And if I want to stay on the unit tangent bundle, there's a restriction. I can't go outwards. And that restriction means you have to be moved perpendicular to the unit vector, tangent to the unit sphere. So V perp means all vectors perpendicular to V. So you get that. So that's kind of helpful. Okay, so that's the sort of very quick introduction to basic geometry. Now that we've got that, I can describe this Liouville measure. And I can describe it in two different ways, which actually give the same measure. So let's have two structures on the unit tangent bundle. The first structure is a Riemannian metric. It's often called the Sasaki metric. There's a Japanese mathematician called Sasaki who wrote several papers studying the properties of this metric, I think in the 1960s. I think the metric had probably already been used earlier, but he made a quite extensive study of it. And it's good to have some name for it. And by the way, there are other ways of constructing Riemannian metrics on the tangent bundle. There's a book by a Japanese mathematician called Yano, which studies about maybe half a dozen of these. They're not quite as numerous as the metrics on Teichmüller space, but getting there. So the Sasaki metric looks like this. I have two vectors, both based at the same. These are tangent vectors to the tangent bundle. That's my effort at writing eta. And what you do is kind of the obvious thing. You take the inner product of the horizontal parts and the inner product of the vertical parts. And what I mean here, of course, is I use the Riemannian metric on E. So these, I know what these are. I now know what this is. And maybe I should use double things or something, but I'll just stick to writing that. The other thing is a symplectic structure. So I've got the same xi and eta, and now I have omega. So you already know from the choice of letter that this is a two form. And what you do is you do the same kind of thing, but I sort of have h with v, and then there's a minus. I think that's h. Okay, it's that. Or maybe it's minus that. I can't remember. You know, one or the other, it doesn't make too much difference. I hope this is the right one. Okay, this is obviously a two form. There's a little bit more to being a symplectic structure. This is supposed to be a closed two form. Okay, well, this one is actually exact. It's closed because it is exact. So in fact, omega is d of some one form that I'll call theta. And so on TV, TEM, theta of xi is, you do the inner product of v with the horizontal part of xi. Remember, v is a vector at the foot point of v, and this horizontal part of xi is also a vector at the foot point of v. So this makes perfectly good sense. And there is a calculation which I have in a tech file, but I'm not going to write on the board today. It fits comfortably onto a page, which shows that this actually works. Well, it works unless I have the wrong sign here. Okay, so we do have a closed two form. And by the way, this structure here with the two form being the derivative of the one form may seem very familiar. There is the cotangent bundle. And there is a canonical one form on the cotangent bundle. And it's really canonical. If I look at the tangent space to the cotangent bundle at a V star and do the same kind of thing, I look at theta of xi, maybe this is theta star because it's the cotangent bundle. What you do is you take the horizontal part of xi, or actually you just take d pi of xi. That's a vector. V star is a covector. It's just waiting for a vector to act on. There's a vector. So you write that. No structure beyond the fact that you have the cotangent bundle. This is canonical. And so you get this one form. That's the coloured chalk. Colour. And then you have omega, which is d of theta. And now there is, if you have a Riemannian metric, there's a translation from cotangent bundle to tangent bundle. Vector v changes into the covector, which is doing in a product with v. So you use this correspondence, you can transport any structure here to stuff over here. Well, if you take the canonical stuff on the cotangent bundle, drag it over with the correspondence, this is what you get. So this is as canonical as you'll have for the Riemannian metric. But obviously if you use a different Riemannian metric, you get a different structure here. Okay, so there's our, we have our metric and we have our symplectic form. So if you have either, actually it's not a symplectic form yet. What have I forgotten? Non-degenerate, yeah. So it's not too bad to forget non-degeneracy. Now the idea is if you have either the Riemannian metric or the hopefully symplectic form, you can create volume with them in the obvious way. And if you'll discover whether your two form is non-degenerate by if you try to create volume with it and you end up with zero, then it was degenerate. And here it is non-degenerate. So our Liouville measure is the natural measure, is the measure defined by, maybe I will write that so it's clear that I'm talking about the Sasaki metric, or by omega. You get the same measure. And you do get a measure. Well, it's quite clear that the construction you do with Riemannian metrics certainly produces a measure. And to see that it's the same and that this is non-degenerate, all I really have to do is exhibit a suitable set of vectors. And so what I do is I have, let's think of a vector. So this is some place in the tangent bundle. And I want to have an orthonormal basis for the tangent space that V lives in. And now I am going to write down some vectors. I'm going to write down 2n vectors. By the way, n, as you've probably guessed, is the dimension of my manifold. So I'm going to write down 2n vectors in TV, Tm. That's 2n is the dimension of tangent bundle. And so I'm actually not going to write down these. I'm going to write them down in this form. And basically, at some point, rather than correspondence, I start abusing something and write equals. I certainly think equals. So I write down E1, comma 0, 0, comma E1, up to En, comma 0, 0, comma En. That's 2n vectors. And if you think about the Sasaki metric, it's really clear that these are all unit vectors. It's equally clear that they're pairwise orthogonal. So there is a Sasaki orthonormal basis. And then if you start plugging them into omega, you get whatever the symplectic equivalent of an orthonormal basis is. Oh, and this is also obviously a basis. So this is, these guys I'll say are orthonormal with respect to both the Sasaki metric and our 2-4. So I don't know what the right word for symplectically orthonormal is, but you know what I mean. If I plug these two into the symplectic form, I get 1. So there are the obvious pairs that give 1. Anything else you do produces 0. And then if you think about the scheme that produces the measure for the Riemannian case, you have some determinant in which you just have 1s on the diagonal. These are 2n by 2n determinants. And in the symplectic case, you have something like that. And you have n of those boxes. You get the same, you get 1 out of both things. So they produce the same volume for this collection of vectors, therefore they're the same volume. So life is good. Okay, and then if you want to move to the unit tangent bundle, there's some sort of stuff you have to do, which I'm going to gloss over. But you have this, well, I can draw a picture of a two-dimensional tangent space, sort of foliated by circles. This is an n-dimensional tangent space foliated by spheres, and you just sort of restrict to the sphere of radius 1 and do some things. So I'll skip those details. So we have our measure. Now, not only is it a nice measure, it's also invariant. So I want to sketch why the measure is invariant. Let's maybe make some space from here. So there are a couple of ways of showing that it's invariant. One of them, which I will probably hint at tomorrow, involves doing calculations that involve the curvature tensor. And the key ingredient is a symmetry of the curvature tensor. For some people, that's, well, there's something kind of mysterious about symmetries of the curvature tensor. So I'm going to show a different way of doing it, which for those who are familiar, have seen even the beginnings of classical mechanics, I probably just have to say the words, the geodesic flow is a Hamiltonian flow. And so the magic here, instead of coming from symmetry of the curvature tensor, comes from Cartan's formula for the derivative of a form. So, well, first of all, what is the vector field that generates the geodesic flow? I'll use capital G. Maybe it's an unusual letter for a vector field, but It's got something to do with geodesic. So, and it's a little unusual to plug a vector in here, but remember this is a vector field. G is a function from Tm to Tm. And GV is just V comma 0. And if you think about the picture that was over there, you can see how this fits the picture. We have V here. This is because the geodesic takes off with initial tangent vector V. And the 0 here, this is because d gamma dot dt is 0. So this has got the sort of geodesic equation plus the initial condition built into it. So that's the vector field that generates the geodesic flow. And then the claim is that this is a Hamiltonian vector field. So to be a Hamiltonian vector field, you have to have a Hamiltonian function. So the function that is relevant here is this one. This is basically kinetic energy. If we think of having a particle of unit mass moving in our Ramanujan world, according to, I think, Newton's first law of motion, it's describing a geodesic, and this is the kinetic energy. So Hamiltonian vector field means if I look at the derivative of the function h, I want to take the derivative at v. And as we've heard several times, there are times when you've got to be careful with parentheses. So this is the derivative of h at v. This is a linear map. And then it acts on a xi, which is in the tangent space at v. And I think I put a minus sign in there. And then this will be that. This means exactly this formula, except with the g of v plugged into the first slot and xi into the second slot. So the idea of the Hamiltonian vector field is you have a Hamiltonian function which has a derivative, and then you turn the derivative, which is a linear map, into a vector field. It's the sort of symplectic equivalent of doing gradient flow. So you kind of use the symplectic form, and you end up here with a vector field that is actually going to be tangent to the level surfaces of H. So you have this formula. And now there are a couple of simple calculations you can make. The first one is, suppose I look at the derivative of H and I apply it to GV. Then what I get is minus omega, I guess. Xi is now GV. I have the same thing in both slots of my 2 form. I get 0. So this says that our G of V is tangent to the level surfaces of H. This says that H is going to stay constant under the flow. That corresponds to the going at constant speed for the geodesic flow. And the second calculation is that omega is invariant. So I'll use the notation L is meant to stand for Lie derivative. So basically I'm seeing how omega changes under the flow for the defined by G. And I'm doing this at V, and I want to get 0. So I now I use Cartan's formula. I have IGV d omega plus di GV omega. This is the magic part. And then life is really easy. D omega is really d theta. And what is IGV? It's dH. And then you look at this formula. dd of anything is 0. So you get 0. So this says that omega is invariant under the geodesic flow. So omega wedge, I guess with n of them, that's the volume, is invariant. So that is the proof. That proves that omega is invariant on the full tangent bundle. There's another step to show that when you restrict to the unit tangent bundle, that the restriction of the measure there is still invariant. I'm going to skip that step, but it's pretty easy based on the fact that all of the sort of different levels in the tangent bundle stay within themselves. And the sort of, this invariant volume is volume in the unit tangent bundle times the sort of projection of the vector transverse to the unit tangent bundle, and that projection stays constant. So it's a pretty short step from this to invariance of the measure on the unit tangent bundle. So we actually have an invariant measure. Great. And I still have 20 minutes or so. So now we have the invariant measure. And now I'm ready to talk about a hyperbolic surface. So let me make some space to do that. So I want to draw a picture which shows why hyperbolic geometry produces hyperbolic behaviour of the geodesic flow. I believe that the use of hyperbolic in these two contexts is kind of independent. And so it's perhaps a lucky coincidence that hyperbolicity produces hyperbolicity. Of the geodesic flow for a hyperbolic surface. This goes all the way back to Hadamard from, I think, around 1898. I really mean 18. This is classical. And I think back then, the phrase they used was exponential dichotomy. And so the idea is if I think about some nearby geodesics, the typical thing they do is diverge exponentially. Except when they don't do that, then they converge exponentially. And so I want to show you a picture of exponential convergence of things. So I think you already know that that's a picture of the upper half plane. This is H2. Actually, the picture works just the same in HN, but maybe the little calculation I'm going to do is clearer in H2. I want to think of two geodesics. They go that way, off to infinity. And maybe one of them goes through I, the other one goes through I plus something, X. And I want to go up a ways. I want to get to e to the ti and e to the ti plus x. And so if I look at the length of these segments, this segment here has length x. in both the Euclidean and the hyperbolic worlds. Up here, you still have Euclidean length x, but since this is a hyperbolic picture, the length is really e to the minus tx. So you can see that the distance is exponentially smaller. And then the real point of the calculation is, there's a reason why I went up to e to the t. What is the hyperbolic length from here to there? Well, I have to do the integral from 1 to t of du over, 1 to e to the t of du over u, which is ln of u, from between e to the t and 1, you get t. So I've flowed these geodesics that are going to the same point at infinity for time t, and the distance between them shrank by the factor e to the minus t. There's your exponential convergence. And actually what I really care about is the distance between those vectors in the unit tangent bundle. But these curves are both pieces of horocycle. All horocycles are the same. They all have the same geodesic curvature, which is 1 or minus 1, depending on how you oriented yourself or disoriented yourself. And so if I have a piece of horocycle that's shrunk, then the distance between these vectors are normal to the horocycle. Yeah, I write my perpendicular symbol sort of the, I guess, the English-speaking way instead of the French way or the European way. The distance between these vectors that are normal to the horocycle is also shrinking exponentially. It's at worst some multiple times the distance between the foot points. So you can see the exponential convergence happening there. And then there is a philosophy about the hyperbolic plane, which is if you want to calculate anything, you draw the picture in the upper half plane and calculate there. And if you want to draw a pretty picture, you draw the point array disk. So now I want a pretty picture. So I have a point on the boundary, another point on the boundary. I have a geodesic joining them. And then my sort of family of geodesics going vertically in this picture becomes geodesics going to that point at infinity. And my horizontal lines become the horocycles. And as you can see, the horocycle is orthogonal to the geodesic. And then there's also a corresponding horocycle for the, so this will be my vector v. There's a corresponding horocycle for the back end of v, also wonderfully orthogonal to the geodesic. And if I follow geodesics going backwards to that point, I get exponential convergence in backwards time. And if I go forwards, I see the exponential divergence. And the typical nearby geodesic has a behaviour that's a combination of the two things. And of course, expansion totally dominates contraction. So the typical nearby geodesic diverges exponentially in both forward and backwards time. And we're really interested in the special ones that converge in forwards time and the special ones that converge in backwards time. So if I look at these horocycles, maybe I should have a new picture in which I will just have two horocycles, and I can make my vectors look a bit more perpendicular to the horocycle. And so this collection, so this may be, there's V. This horocycle I could call the stable horocycle for V. And then the collection of vectors, these are the unit normals to HSV on the same side as V. So that this is important. This object is really fundamental in understanding the dynamics. And the point is that if V and V dash, well, if, let's say if V and V dash are in the WSW, the distance from phi t v to phi t v dash converges to 0 as t goes to infinity. In fact, it converges exponentially to 0. I could say less than or equal to some constant times e to the minus t. And then there is also, you have HU of V and WU of V, and the corresponding statement is, would be distance from phi minus TV, phi minus TV dash. So this is with V dash in WU. W. So I have so this is called a stable manifold, and this is an unstable manifold. And they're the fundamental things that help us understand the behaviour. And you can see that they come straight out of the hyperbolic geometry. Okay, so I have drawn a picture for one vector in the hyperbolic plane. I can do this picture for any vector in the hyperbolic plane. What I really want to do is to think now of a compact surface and think of this as the universal cover of the compact surface. So really I want to think of a vector v down here, and the v that I had up here is the a lift of v. Well, I have multiple liftings of v, but they're just connected by symmetries. And so it doesn't matter which lift of v I pick, when I make this construction, I get an isometric copy of the construction from another lift. And so what I have up here projects to something down in the tangent bundle. And then if I do it for a different vector w, I get ws of v, ws of w. So for each vector in the unit tangent bundle, let's find some space and some new chalk. I think we can maybe start here. For each V in, let's have a bit of context. M is going to be a closed hyperbolic surface. Well, perhaps it should be S, because S has been surfaced throughout the week. And so for each V in T1S, we have WS of V and WU of V. And these have this property that if I take two vectors in here and flow them forward, those vectors move closer and closer to each other. In fact, they approach exponentially under the geodesic flow. And here, two vectors in here approach exponentially under backwards geodesic flow. And these things, they give actually foliations of T1M, T1S. And then there's a third foliation. There is the orbit foliation. So I want to draw a picture, a somewhat schematic picture. And it's going to be a picture in the unit tangent bundle of our hyperbolic surface. So here's a picture in this is a three-dimensional picture because the surface is two-dimensional and there's one dimension of unit vectors. And so I have V, which looks like that, because this is a picture in the unit tangent bundle. And then you have the orbit of V. That's the leaf of the orbit foliation. You have WS of V, and you have WU of V. And if I look at orbits which go through let's take WS of V. Maybe I can try to get fancy and use some colour. Let's hope. Is blue reasonably visible? And are they okay? Can you see them? Okay. So let's have blue for stable. If I take some blue trajectories, they come in exponentially in future time. And there are unstable trajectories. They come in exponentially in backwards time. So we have a foliation that looks like that. Okay, now I have the setup that I need to try to prove ergodicity. So the proof I want to show you is due to Eberhard-Hopf. And this is usually called the Hopf argument. Eberhard-Hopf is not Heinz-Hopf. They were both active in the 1930s, both great mathematicians, but this is Eberhard. So he wants to show that the geodesic flow is ergodic. By the way, this is not the original proof of ergodicity for hyperbolic surfaces. The very first proof was actually for a special class of hyperbolic surfaces, and it used the kind of coding argument that we saw in Professor Dani's lecture yesterday, the sort of coding of geodesics. But this is the argument that generalizes to higher dimensions and to a lot of other situations. It's also a beautiful and simple argument. So first of all, I'm going to prove something much weaker than what I need to prove. Let us suppose that f from T1s to R is invariant. That's what I have to investigate. Then I'm also going to assume that it's continuous. And now I'm going to show you that this function is actually constant. And why is it constant? Well, if I start off at V, I can move, there are three directions in which I can move. I can go along orbits, I can go stably, I can go unstably. I think I forgot to say that these foliations are transverse to one another. And it's also true that flow and stable sort of fit together nicely to give a kind of flow, combination of flow and stable, and the same with unstable and flow. Stable and unstable do not integrate to give surfaces. But I can get anywhere I want by going flow, stable, unstable, and maybe repeating if I have to. So f is obviously constant on orbits. Why? Well, because it's invariant. That's the whole meaning of being invariant. But now f is also constant on stable leaves. Why is it constant on stable leaves? Well, here are two places on the same stable leaf. We look at their orbits. We follow as we go along these orbits, the invariant function is staying constant. The orbits are getting closer and closer together. So at some point in the future, when they're extremely close, the values of the continuous function at these extremely nearby points. They've got to be extremely close. I did mention that this was a closed hyperbolic surface. So our continuous function is not just continuous, it's uniformly continuous. So we wait till these things are uniformly close. The values of the invariant function are uniformly close. Pretty soon we realize that our invariant function is constant on the stable leaf. Okay, well, anything you can do for stable leaves, you can do for unstable leaves. You just have to reverse time. So there's your proof. Okay, well, that was too easy. But this idea of looking at saying that if I've got things that are getting closer and closer together, then something continuous becomes very much the same. That's the takeaway from here. And that's the heart of Hoff's argument. So now he has to deal with not just a continuous invariant function. Let's have f be, let's see, here we have, I will assume that f from T1S to is, I'll assume it's L1. Okay, well now I have to use an important theorem. This is the Birkhoff-Ergodic theorem. I make no apologies for using it because it's one of the great theorems in Ergodic theorem. Actually, it's just a great theorem. So I can take, I suppose I have, actually let's just have x. And I have, I can have the phi sub t from x to x, and mu is phi sub t invariant. Actually, yeah. So I have a flow on some space with an invariant probability measure. And now if I pick a point x in x, I can write down the following definition. Limit as big T goes to infinity, 1 over big T integral from 0 to t of f of phi sub t of x dt. I can write down a corresponding thing. So this means I look at the x, I flow forward for time big T, and I average what I see along that piece of orbit in the obvious way. And then I can do a backwards average, and then I take a limit as T goes to infinity. And there's almost the same thing f of phi minus tx dt. So I can have these two averages. These are called Birkhoff averages. Okay, well, just because I wrote the word limit on the board doesn't mean these things actually exist. And it's easy to cook up examples of orbits for which these averages just do not exist. And the importance of Birkhoff's theorem is that, so what Birkhoff says is f hat plus f hat minus x, they are defined and equal for mu almost every x. So these, in the context of where we've got the invariant measure, these are sensible things to talk about. They exist almost everywhere, which is as good as anything ever gets in the measure theoretic world. And they're the same. And that part is a little dodgy, but they're as close to being the same as they're going to get. And so now we try to copy the sort of baby Hoff argument that we had. We now try to do the real Hoff argument. So again, we want to go through the same, oh, wait a minute, there's something I have to do first. Great, I've defined Birkhoff averages. Now, suppose I had an invariant function. It would be its own Birkhoff average up to measure 0. And so I want to prove that rather than trying to prove that invariant functions are almost everywhere constant, we will show that Birkhoff averages are almost everywhere constant. So when you think about when you apply this to the Birkhoff average of an invariant function, we'll get what we want to know. And now the idea is I don't have to think about the Birkhoff average of every possible f. It's enough to work with some dense class of f's, because the map that takes f to the f goes to f hat plus or to f hat minus. Those maps are actually linear and have norm 1. So if I want to show that the maps go into the space of almost everywhere constant things, it's enough to do it for a dense set of f's. So I assume that f is continuous. And show that the Birkhoff average of a continuous function is almost everywhere constant. Okay, now we go through the 3 types of foliation. Well, along an orbit, everything in sight is going to be constant. So, well, along the orbit, it's clear that, so f hat plus f hat minus a constant along orbits. That's easy to see. Well, it's actually very easy to see that f hat plus is constant along a WS leaf. And I just go back and look at my picture of 2 things in the WS leaf and think about Birkhoff averaging along those blue orbits. Well, for a while, things are very different. But then these get very close, and they stay very close. So virtually all of your average is coming from things that are very close. And so it's really pretty obvious that this function is constant along WS leaves. And the backwards average is constant along WU leaves. So we're almost there, except that we have one type of Birkhoff average here and the other type here. Now what I do is think of a picture of my unit tangent bundle. Let me draw maybe a foliation by WU leaves. And maybe let's introduce a set G. So let me say for all X in a set G with full measure. So this G is not the generator of the geodesic flow. This is G for Gord. So I have my full measure set G. I have a foliation by WU leaves. This is a very nice foliation. And these, the leaves are horocycles equipped with normals. Horocycles vary in a nice smooth way. This is a smooth foliation with smooth leaves. I can use some theorem like Fubini's theorem. I think that's the right word. And say, well, look, I've got a set of full measure. And look at the intersection of this set. I can find the volume of the set by intersecting it with leaves and then doing an integral of the measures of those intersections. And that will allow me to find a leaf, a WU leaf, in which almost every point belongs to G. In fact, your typical, virtually almost all WU leaves have almost all points in them in G. So I take a leaf in which almost entirely in G. I've got all these points on it. I think I've drawn them. Yeah, I've got these points on it which belong to G. Through them, I draw the staples. So I start off by saying my f hat minus is constant along here. I switch to f hat plus at all the points in G, because I can switch. Then I go out along the WS sleeves. F hat plus is constant along them, and then I flow. And what I will end up with is a full measure set of orbits with the same value for f hat plus. So there's my almost everywhere constancy of f hat plus. And so that's the end of Hoff's argument. It's very simple. So the next lecture is going to be doing the same argument again in variable curvature. And it's not going to be quite as simple. If you want an exercise, you can try to think of what part of this argument is going to be difficult next time. Yeah, let me finish there. Thank you.